Alright, so yeah, in this video we are going to understand how to make a proportional logic in a liquid level control. That is the last lesson of today, but I'll give you a brief what is that proportional control. So this is a small demo and then further we will program it. So if you see here, we have this level right now at 2.9, okay, and this potentiometer is my set point which I change from here. Okay, this is the fill valve which is 0% open, which means it's closed. Also the discharge valve is 0% open, which means it's closed. So we have the filling from the top and discharge from the bottom. There is a level meter whose indication is here 2.9, which means 29%. Alright, now if I say I need more water in the tank, I will increase my set point. I make it to 6.2. and you will see the valve is 100% open and this is increasing, and as this is reaching to the set point, the valve is proportionally decreasing. Right, this is automatic. So the valve level, the filling of this valve is getting close now once it reaches the level, so which is 6.2. now if I say I want to decrease the level, you will see drainage valve is open proportionally and this is going to close once I reach the set point. So this is called proportional control, how you can control the actuation of your valve proportionally using a proportional logic. This is what we are going to learn today. However, the first objective of today is we have to scale the level meter ID30 in TIA in percentage. So the first task of today is, if you see here, we have this level meter. We have to scale its value. Right now the value is from the range 0 to 10. Right now it's 4.6. At maximum level it will be 10 and minimum it will be 0. So we have to scale this value in 0 to 10, 0 to 10 to 0 to 100%, and the height which is 0 to 300 centimeter. So if you see here, the height is mentioned here, which is 300, and if you see the bottom, it's 0. So we have to scale this value and we have to see how we can do that in TIA.
So can I ask a question?
Yeah, sure.
So what is ID30?
Okay, yeah. ID30 is my, if you go to here drivers, ID30 is a resistor where we have connected a level meter. So the value of level meter will come in a resistor which is inside the PLC, ID30. And the potentiometer, which we don't need right now, I'll remove it. Then in the output we have a fill valve and we have a drainage valve or discharge valve, and their respective resistor is QD30 and QD34. Now this I represent input, D represent double. So that's why after 30 it is 34, because it's occupying 4 registers, 30, 31, 32, 33. Similarly here, this double resistor occupy 4 registers, 30, 31, 32, 33. Okay, this resistor is of 64 bits. That's why one resistor is 16 bits. So multiple of 4, it's 64, so it's occupying 4 resistors. Okay, so the task says we have to scale the value of ID30, which means the level meter. So we'll go back to our PLC and we have to write this in SCL, okay, because we are learning how to write a code in SCL, which is a programming language in Siemens widely used. So let's see how we can do that. So for that, the first step is, if you're on the program block, you have to click add new block and go to functions and take an SCL language. However, you can select ladder and FBD as well, but go to SCL and click OK. Once you click OK, you will find this window, and this window is from this block, and we can also rename this block and name it as scaling, because here we are going to create our own function, right? So the function says you have to scale the value to 100%. Now we know that if I write here, our ID30 is getting a value of 0 to 10. Now we need to scale it to 0 to 100%. Okay, so the simple logic is we need a multiplication factor of 10, because if you multiply 10.0 with 10, it is 100. So what we can do is we have to first define some variables. All right.
Okay, sir.
So in the input, what we have the value coming from sensor. All right. And that value which is coming from sensor isn't real, because if you see here, it says it's a real value. So you have to make the data type real. The sensor, you can write ID30, you can write sensor, you can write ultrasonic or whatever input. So this is irrelevant what name you give here. Now we need an output, because after scaling you need to show the value. So here we will write scaled sensor. This is a scaled value which will be in percentage, and this will also a real value. So we have defined two variables. So we have to multiply input with 10 and store in the output. So here, yeah.
So do we have other options on data type?
Yes, of course. Yeah, we have it here, all the options. We have real, word, integer, double integer, time, and this is hardware interfaces, character, boolean, bytes. We have all the data types. Okay. So now, simple thing is you have to write sensor, and it will automatically, it should automatically, it's not showing, but anyways, you can write, this is a symbol. Wait, let me zoom it for you. This is a symbol of addressing, and if you take sensor, it will automatically help you to write it, and then you have to add colon equivalent to a sensor value. Sorry, this will come to the right. Here will come scaled value, because the output here comes on the left. Scaled value is your 10 multiple of sensor. Okay, so whatever you multiply with sensor will be in your scale sensor, and you have to write semicolon. So once you write this code, and when you go back to your main logic, just drag the scaling function here, and you will see your own customized block, and in this block you have this coding. So you have created your own function which you are using in your main logic. Now here, what was the sensor? Our sensor was ID30, so just put ID30, and the output, now the output you can use in a data register, or I can give you one more option. If you go back to your environment, we can display this value in a digital display here. Here I can rename that to level in percentage. So this is level in percentage. Go back to drivers, and we have two outputs. To increase these outputs, go to configuration, and this is the analog outputs. Make 3. Go back here. You have one more, and here this is the level in percentage. Connect this one to your extra output, and this is QD38, and this is in double int. So just go to your PLC, just write QD38. Okay, now let's download this logic in our PLC, and let's see the results. Alright, so right now you can see this is some percentage of level, and here level is 0.0. Let's start the process. Okay, I will just force the value here because we are not having a proportional value inside, and we have to make sure this should be working. Yeah, QD38 is here. Oh, wait a second. I should change its data type as well. Here you have a conversion option to convert something from real to integer, because our value was in real, so you can right here, scaled sensor. This is a conversion option. Wait a second. Semicolon, return function to value. Dint, okay, it was dint. Should work. Okay, let me try one thing. Let me check how much value we're getting in PLC. However, we are getting the value in percentage here, but there's some restriction in using the real values in the display. But if you use an HMI, this is just a software. If you use an HMI, and you can read here the values coming in percentage. So maybe you can ignore the software part, but we are getting the value in percentage in our PLC, which we can display in the HMI. So this is just a software bug because I cannot change this integer of software to real, which I want, but this is not an option here, so I will just put that here. Okay, are you guys getting me? Okay, so the task one was to have percentage. Now the second scaling was in height, which is 0 to 300. Okay, now we have to go back to our scaling logic, and we have to also scale this in range of 0 to 300. Now how can you scale the value of 0 to 10 to 0 to 300? Can you guess? Guys, are you there with me?
Yeah, we're here.
Hi Kevin. So yeah.
Yes, actually microphone won't be over.
Alright. So can you guess how can you scale the value to 0 to 300 from 0 to 10? We are getting 0 to 10 volts in the PLC, and we need to show the range in centimeter. So you have to convert the range of 0 to 10.0 to 0 to 300.
Just multiply with 32.
Yeah, we just have to multiply. So I will take one more output, because right now it's scaled in centimeter. That is also real, and here we will put the output first, scale in centimeter, which is equivalent to your ID, the sensor, which is ID 30 multiplied by 30. That's it. Because if the value is 10 here, we need the value 300. So if you see the multiplication factor, 300 divided by 10 is 30, and you have 30 here. So we have scaled in centimeter. Now the good thing is, if you go back to your main logic, you have to update your block. So right click and update block call, click OK. So you have scaled in centimeter, and I'm going to read this value in a data register, which could be MD30. Okay. So let's see that now in centimeter. So you can see right now it's 190 centimeter, and if you see here, it would be approximately 190. Okay, so if you increase it, the value will be increased here. You will see the value of percentage being increased here, and also the centimeter. Okay, this is very easy just to scale the values. We have to just read the sensor and see the multiplication factor and just write the code, make your own function and display it here. I hope this part is clear.
Yes, sir.
Okay, Kevin, you there? Just meet? Yeah?
Yes, sir.
Alright, so let's proceed to the next task. Display the scaled value on the panel. However, we tried, but unfortunately we don't have a real format in the panel here, so we cannot display it in the real values. So we'll come to that part a bit later. So the next is interesting question. It says make an auto function using SCL code such that it fills the tank in such a way that if tank level is less than 40%, we will read ID 30. If it is less than 40%, we have to make the fill valve opening 100%. Now the fill valve opening is this one. This is the fill valve. This should be 100% if the level is below 40%. Now it says if the level is above 40% and less than 80%, between 40 and 80, then fill valve opening should be 50%. And if the level is more than 80%, it means it's about to fill. The fill valve should be closed or should be 0%. So these are the three conditions we have given, and it says use toggle button to drain the valve at 50% flow rate. Okay, now if you have any questions regarding, you can ask me in between. And this code we can write using if else statement, and it's very easy. So what I'll do is I'll just copy this condition and we will put it here. So this was the scaled logic. We are not going to interrupt it. We'll go to program and create a new block. Again, function block, and we can call it, let's call it semi-automatic or automatic control on-off. This is not proportional. This is an on-off control. We'll come to proportional after that. So this is again the same window, and I will write comment here for you to understand. The question comes here. Okay, so the first sentence says if the level is less than 40%. Now we know that we are getting the level in percentage in our resistor. If you see here, QD38, this is in percentage. Okay, so we will go back to automatic control. So let's define the inputs. So in inputs we have level in percentage. Okay, and what we have in input, that's it. We have to compare the only input, which is level in percentage, and then we have to write the output, which was our drain valve or fill valve. Okay, so in output I will write fill valve. The first step of writing the code is always to define your input and outputs. Now the level in percentage was in real, so mention real. Output was in real, so it will be real. Now if you are good with your C++ skills, you might know how to write an if and else statement. It's very easy here as well. One option is you can take the instruction, go to program control and use if else syntax from here, or you can write by yourself. So since we are having three conditions, I'm going to take if else and else if. Okay, we have to write nested loops. Okay, so I will take this one and drag it here so that we can have multiple conditions here. The first condition says if tank level is less than 40%. So here it will come level in percentage. So first will be level in percentage. If this is less, put the lesser sign. 40%, we can write 40.0. Okay, then what should happen? It says fill valve should open 100%. Now the fill valve is here. Write fill valve. It should be 100%, means greater than, equivalent to. Now fill valve, if you see in our factory IO, is having a value 0 to 10 volt. Okay, so you don't have to write 100 here. You just write 10.0 and put semicolon. Okay, because our valve is not scaled to 0 to 100%. We have only scaled the input, not the outputs. So you just write 10.0. This will work. Okay. Now else if the level is greater than 40 and less than 80. So again, maybe I can copy that. Is greater than 40, so I'll change the sign. And less than 80, so I will copy that. And now it says AND. AND is an AND gate, but practically you can here write simply AND. This is how you can easily write AND gate in this coding, or you can also write the symbol AND. Okay, so however you like. And if this is less than 80%, okay, then what should happen? Fill valve should be 50% open. So copy this code, put here 50% is 5. Okay, because again the scale is not 0 to 100, it's 0 to 5. Else the third situation says if the level is above 80%, valve should be 0%, valve should be off. So I will copy this part, above 80, I can also write here else if, that will be more suitable. Then the valve should be closed, so just put here and put here 0, and now our logic is ready. Is there any doubt in this one?
Okay.
Okay, so this is the logic for these 3 situations. Okay, but we still have to write the code for toggle button to drain the level. Okay, now if we come back to environment, we can use this first button, this first start button for draining. Okay, so let's see its connections. This is not connected anywhere, so we can connect the start button. Okay, it's here, I0.0. Okay, so we have to read I0.0. If this button is pressed, we have to start the draining at 50%. Okay, so we have one more output, drain valve. We'll give the address to these valves later. We are just defining the variables. So I will cut this comment from here and put it here. Okay, now if button is on, which means button is a boolean, so we have to take the input and we will write drain input, or I don't know, drain button. Okay, and this is boolean because button is always on or off. Okay, so now here again we'll write if drain button, so the address is true, you can write equivalent to 1 is high. Then what should happen? The drain valve should be 50%. So drain valve is, now if you notice this symbol here, this means the value on the right will go to the value on the left, but if I don't use the column, this is comparing it. Okay, drain valve is 5.0. Okay, so these 2 lines is the logic for if the button is pressed, then drain valve will be 50% open. Now if you see this error comes because the loop is not closed. So I will write end if. Now the loop is closed, so there is no red underline. It means our code is correct. You can also compile it, so this is okay. Now just go back to main logic and just drag your code here, and you will see your block which says level in percentage, drain button, fill valve, drain valve. So level in percentage, as I told you, was here, QD38. Just write QD38, and drain button was I0.0. So just put I0.0, press enter. Fill valve and drain valve. Fill valve is, we can put it, wait, oh, it's already here. QD30 is fill valve, QD34 is drain valve or discharge valve. Just write QD30, QD34, So everything is okay. Download the logic and let's see the results. Any doubt here before we proceed? Okay, so let's see the operation. I will release this force because now we are controlling, and play. So since the level is below 40%, you can see the level here below 4, the valve is 100% open. When the level reach between 4 to 8, this will be 50%. You can see it's changed to 50%. And when the level is above 80, you will notice this will be off. Sometimes the programming in SCL is easy because you can make your own function and you can easily modify it and update it and use it in your own way. So above 80 it should be off if our logic is correct. Yeah, that's pretty much okay. Any doubt in this one? This is just following the code which we wrote here. Yeah, maybe you can also monitor that here. Yes, you can. So if you just want to see one more time, you can see the results here, which result is true, which is false. So this if statement is true, which means the level is above 80%. So this result is true, which makes the fill valve to 0. Okay, now we have to check the drain button here. So just go back and see the panel, and when you press this one, you will find your discharge is open by 50%. And the interesting thing is, you will see the filling has been started by 50% because the level goes below 8. So what is happening here, we are using the liquid and it is also controlling the level. So we have maintained a certain level in the tank such that even if we are using the liquid, we are discharging the liquid, our level is maintained. We have liquid all the time. Now the interesting part is, if I increase the level of this discharge valve, if I make it like 75%, so what will happen? The level will goes down because filling is 50% and draining is 75%. The level eventually will go down. So let's try that. I will write 7.5 and download the logic. And now you will notice the drainage is more than filling. So level is going down. Okay. So what will happen if it goes before 4? The filling will be 100% as per our logic. So even then, if the filling is more than draining, our level is maintained. You will just notice now. This is like a step control or on-off control of liquid. This is not proportional. So let it go below 4. And now you have seen the filling is 100%. But then again it goes to 5 the moment it reaches above 4. You see this thing? This is one of the disadvantage if we use proportional control because we have on-off situation here. Are you getting me?
Yes, sir.
So this situation we can avoid using proportional control because this is harmful for the equipment. If you make something on to 100% then 50%, we have to have a proportional control of the valve, which is a smooth operation. So to avoid this situation, we go for proportional control. But before going to proportional, I want you guys to understand these loops, if and else, otherwise it will be difficult for you to proceed. Okay. You can also make a button here for drainage. You can use like a low drainage or fast drainage. Suppose if I press this low drainage or slow drainage, it should open the valve with 25%. If I click on the fast drainage, it should open the valve with 75%. Okay, can you do that? Can you tell me how I can do it? Like I want to have one more button here If that button goes high, the drainage should be 25%. If the other button goes high, the drainage should be 75%, which is happening right now, but I need one more button for 25%. What should I do?
You said we have to take one more input.
We have to take one more button here, and then we have to write the same code. If that button is high, it should be 2.5.
Yes.
But then we have to interlock it. If somebody presses both the buttons, nothing should happen. Or you can define what should happen if somebody presses both buttons. Or it should be 100%, I don't know. So with this, you can define using if and else statement as well. So maybe you can take it as your homework, I don't know, if you like having homeworks. Otherwise, we can proceed. Yeah, so this was automatic on-off control. And now next is the main part. It says make an arrangement to change the set point of water level using potentiometer 0 to 100% and write a code in SCL to achieve the set point using only proportional control. Automatic proportional. Now if you heard about PID control, proportional is a part of PID control. And we generally use only proportional control if your rate of change of error is very slow. Now what do I mean by that? Here, if I start filling the tank, it's a huge tank. And when you start filling it, the level increases slowly. So in that case, we can use only proportional control and it will work. In case if we have some other scenario, for example, I have shown you in the last lesson that we have a ball in which ball moves up and down by a flow of air. So in that case, because of gravity and because of air, ball movement is very sensitive because it was very lightweight. In that case, we have to use PID, but in this case, we can only use proportional control. So let's go back to our main logic and we delete this automatic control block from here. But don't worry, the block is already here. We are just not using it. So I'll go to program block and add a new block. Go to functions, and here you will write proportional control logic. Okay, now here we have to write the code. Now if you know, in PID we always deal with errors. Okay, can you tell me what would be the error in our situation? In this situation, what could be the error? Anyone? In a control system, what is the error? In any control system, we have a basic control system where we have input, then we have controller. Yeah, difference, exactly. So the error will be the difference between what the user wants and what's the actual feedback. That is the error. So in our case, let's first write how we can calculate the error. So in error, we need the user input. So let's define the input and let's call it set point. Set point is, yeah.
Do we need any feedback in this?
Yes, of course. The feedback is the level meter. The level meter which is showing us the level is the feedback, because this is the sensor which is giving us the value. Okay.
That will give the differences between.
Exactly. So I will write sensor, and both these values are in real. Okay. Now the error will be the difference between that. So let's define the error as a temporary variable, because temporary variables are those which we use just for calculations in our logic. So I will write error here, and error is also real. Cool. So I will write error, and it should shows the anyways. Error is equivalent to set point minus sensor. So set point minus sensor. This is the error, and this should always in temporary variable, because this keeps on changing. Okay. Now after the error, you have to write a proportional logic. Now proportional logic means, if you know the proportional control, it will only actuate the output based on how much is the error. If the error is more, it will automatically make the fill valve 100% open. If the error is less, it will reduce the fill valve by some percentage, which depends on the error. So proportional control is directly proportional to the error. So what we write here is, let's give a comment. Proportional control. Now in proportional control there is a term called gain, right? Suppose if the error is 50% and the proportional output is 50%, the gain is 1. Alright, but if you increase the gain, it will quickly reduce the error. Okay, that's how you can relate the gain of proportional control help you to quickly overcome the error. So we will see how we can change the gain. So as of now, I will give a variable here input, which is kp. Kp is in real, and this I'll put a comment proportional gain. We will see the result of different gains in our logic. Okay, so in proportional control, now we need an output. So here I am writing an output as we have output drain valve. Okay, and we also have an output filling valve. And we will also write an output which is you know, in our control system, generally we refer to the PID output or proportional gain output by the symbol U or by letter U. This is very common in control systems. So I will write here, this is our proportional controller output. That will be suitable. But we don't need U in here, we just need U in temporary because it's the calculation output. Okay. Oh, there is no paste option. Okay. Okay. I will tell you what U is. So proportional control output. Now that output will be U. This is the output of the controller, and that should be equivalent to your error multiplied by the gain, which is Kp. Now try to understand that if the gain is 1, okay, and if the error is 50%, the output of controller will be 50%. You getting me? If the gain is 2, the output of controller will be 50% into 200%. It will open the valve by 100%. But we'll see more clearly once we start running the simulations. So now comes the output. Now the output, we have two outputs. So this is really important, you have to understand. The filling output, which is the filling valve, is directly proportional to your PID proportional controller output. So I will just write equivalent to U. Okay, because the output directly goes to filling, because we are reading when set point is less than sensor. It means suppose my set point is 100% and the sensor is at 80%. What do we need? We need to fill the valve. So the error was 20%, so that 20% directly is equivalent to filling valve. So in this case, this is equivalent to your proportional output, but this will be inversely proportional to your draining output. So in draining valve, I will not take U, but I will take minus U. Why did I took minus? Because if your set point, now try to understand, if your set point, let's say it's 50%, I will put here, give you an example. If set point is 50% and feedback or level is 100%, in that case, what will be the error? 50 minus 100 is minus 50. So if I give minus 50 to drain valve, nothing works in minus, you know. The minus will be multiplied by this minus, it will be plus 50. And level is 100, set point is 50, it should drain the valve. So drain valve will be open by 50%, and here error is minus 50, so this will be closed, because if you give something in minus to a filling valve, it will be closed. So this works opposite to each other. Does that make sense? You will see it. You will see it. Let me just download this logic. So this is the only logic we need to write with proportional control. And let's download this one. and let's see the results. Okay, oh sorry, I have to do one more thing. Just drag your proportional logic here. Okay, set point. Now set point, let's take it from the panel, and here I can use this as set point. Let's see where it is connected. Potentiometer. If you want, I can rename it to set point to avoid confusions. Okay, so the set point is ID 34. So, oops, sorry. Sensor was ID 30 as before. Kp is the gain, so let me put 2.0. 2 is the gain. Drain valve was QD30, and filling valve was QD34. We can still confirm it. Yeah, that's great. Okay, everything is cool. So now let's go to download. Oh, what is that? Okay, online. Wait, something happened here. I think we changed this one. It was MD30 before, maybe. Okay, so let me refresh it. So right now the set point is 0. Let me reduce it. And set point is 0, level is 0, so nothing is happening. There is some noise, so you can see some liquid is coming because some noise is there. So we can remove, ignore that. Let's come to proportional logic. Go online, and now I'm going to give some set point here. Oops, sorry. Should be, oh dear. Okay, so I'm going to give a set point of, let's say, 26%. Wait. What did I do? Filling valve is okay. It's working in reverse. What's the problem? QD30, QD34. Oh, sorry, this was 34. I just mismatched the outputs because it was drained before. So QD34 here and 30 here. Cool. Okay. Coming back to this one. Alright, now you will see the filling valve is on and it's trying to fill the valve, fill the tank, and it will go up to 2.6. This is a level meter and this is a set point. And because the set point is below the feedback, that's why this is increasing the valve, and as it is reaching this value, you can see this is proportionally decreasing. Why? Because our error is decreasing, and if error is decreasing, the output is decreasing because this is directly proportional to error, and the gain is fixed in this case. Are you getting this one? Guys?
Yes, sir. Yeah.
Let me just explain again. If I increase the set point 67%, this is increased proportionally fill valve, and as the level is increasing, this is decreasing because I said it's proportional to the error. Okay, and
Right,
if you notice now, it is taking time to reach the set point. This is a slow operation. Okay, now there comes the importance of gain. If you notice that it is at 5.8 and it will take a minute to reach 6.7, if you want a quick action, you have to increase the Kp, increase the gain. So if you see here, gain is 2. Now you have seen the response, right? Let's see what happens if we need a lesser value. So I'm going to reduce the set point, and now you will see drainage is on because the error is in minus. And when the minus multiply with the minus of the drainage in automatic control, the drainage goes on. That's why we use the minus, to make the drainage on. If we don't use the minus, both the drainage and fill valve will be open, which will not make any sense to proportional logic. If it's not clear, I can explain you again, but if you stay silent, I don't know you know, if you're getting it or if you're not getting it.
Now we're getting it.
All right.
We're getting it.
All right. Now let's see the response by increasing the gain. You will see a quicker response. So let's make it 5.0. Okay. Let's download it. And now this is going to reshare. Let me increase to 8.2. And you will notice it will reach quickly than before. I mean, rate of change of error has been reduced. Error is reducing. You can see the response is quicker, right? This happens when you increase the gain. Gain increases the rate of reducing the error in proportional control. Okay, it will quickly reach to 8.2, but still proportional. And this gain will also affect the drainage. Now 5.8, you can see how quickly drainage response is there. Let's increase it more. Let's make it 20 and download this one. Okay, now let's increase to, oh sorry, I made it 0. Okay, you can see that I made it 0 and this is decreasing. So this will be empty. The valve is 100% open, even and when the value is 20. But if you increase the gain at such level, it will be problematic. We will see that. So let's say we need 18%. This valve is 100% open and quickly closing. Now you will notice that level has been increased to 1.9. Although it will be compensated by drainage, but there is an overshoot. Okay, so in proportional control, if you increase the gain more, you will get an overshoot. Let me explain you what is an overshoot here. If we take a presentation, suppose you have I don't have a paper and pen here, so I would explain it using the PowerPoint. Suppose your set point is 50%. So that's my set point. Okay, and I will put here a comment 50%. And if our proportional gain, when we saw the first time, it was when KP was 10, which was pretty much okay. I will change its color. When KP was 10, we were actually getting the value. Let me try a slideshow. Yeah, that would be great. So when KP was 10, I need a pen. Yeah, we were getting the value we're reaching perfectly fine like this. Okay, but when we increase the KP, this was 0. Let's imagine this is 0 and this is the output of filling. Okay, but when we increase the KP to, let's say we increase it to 20, in that case we had an overshoot like this one. Okay, this overshoot is not required. This is very dangerous in control system. We don't need overshoots. We need a good proportional control so that it will not overshoot the set point. So to avoid this area, we have to reduce the gain. So that's the gameplay, what you do in control system. You reduce the gain to reduce the overshoots. Okay, that's why our suitable gain would be around 10 to 15. And if we do that one, you will notice there will no overshoot here. So level is 50%, it will reach 50 and this valve will be closed. It will not go beyond 50. or 5. Yeah, you will notice here it will close the moment it reaches 5. So there is no overshoot. The level is exactly at 50%. But if we make it 20, the level goes to 5.1 or 5.2, and then it comes back. Although it comes back, but that's not required. We don't need overshoots. Okay, so this was proportional control logic, and the logic is here. If you want, you can write it. I don't know. Any questions regarding that? The next was like just you have to install a potentiometer in panel for the gain. I think there is some problem in your mic because I'm listening my own voice again.
Echo.
Okay, so next is we have to change the gain using potentiometer. That's the very easiest one. You just have to take one more input. Maybe you can duplicate that one, and I will put it here. Instead of potentiometer 2, I will write Kp, which is our gain, and the task says we have to make it to minimum and maximum limit. So minimum limit, let's put it 1, because if you put Kp 0, that is not acceptable, and the maximum limit should be, let's say, 10. Okay, so you have to again write an if and else statement to make the minimum and maximum limit between 0 to 10, and for that you will take the input here. If you don't see here, you can take one more input in your configuration, and you have an input, and put Kp here. Now this is in real, so you have to again make a scaling code in the SCL to check if the input and output range should be only between 1 to 10. Okay, 1 to 10 or 1 to 15. So coming back here, I would like to give you this as a homework. If you can write a scaling here, you just have to make sure the input ID 38, this is coming in 0 to 10.0. You have to convert this range to 1 to 10. So how will you do that? This is a kind of homework. If you do it, that would be great, because next what we are going to do will be a little more advanced than today's lesson. All right, if you have any doubt, you can ask me, otherwise we will close the session.
So where can I get at the simulation software?
Oh yeah, very good question. This is a factory IO software, and if you want to link it with Siemens IO, you need to purchase the license. I can show you the license information in our website.
Okay.
Because this, although this you will have a 30 days trial version for free, which you can download from our website. If you go to the starter edition, you can try the 30 days free version. Link should be here. Yeah, you can download the software from here, which is for 30 days trial version for free. But if you like to extend the validity, you can purchase the license. Now we have different license. If you want to just use control IO, all right, I'll show you here. This logic you can also design without Siemens. If you go to the driver, go to control IO, it says it is starting. Yeah, here you can make the logic in this software, but the problem is it only supports functional block. Like you will have function blocks, you will not have what we were doing in Siemens. This software has small limitation, but this is not I don't know, if you're good with FPDs, you can use this software for making PID logics. There also you have addition, subtraction, multiplication, and then timers, counters, like this AND operation. This is RS flip-flops, SR flip-flop, set reset. But if you like to link it with Siemens, then you have to have a Siemens driver, which comes here. The Siemens edition is this one. We have two editions. One is a lifetime validity, which costs $419, and one is a 1-year license, which costs $140. So if you have a Siemens edition, you can link your software with Siemens hardwares, but if you just want to use the simulation as I'm using, you can also do that.
Okay.
So this is the pricing. Yeah. So it's up to
Do
you.
you have external hardware to use your factory I/O, or you just need your laptop?
Oh, you can use your laptop. Like this driver, which is a Siemens driver, supports the hardware but also supports the software. If you see these two, PLC Sim V5, V13 and V14, I'm using PLC Sim here. I'm not using any PLC right now for this explanation, for this logic. I'm just using the software. So it's up to you. If you have the software, just install it and you can link it. Now to link the software of Factory I/O with Siemens TIA, there is just one logic you have to write in SCL, which is this one. I can give you this logic, just make a function, and this will link your Siemens TIA to Factory I/O. You just have to select Siemens PLC Sim here. Now since I'm using the ultimate version, I have all the drivers of Ellen Bradley, Control IO, Modbus, Siemens. But if you buy the Siemens, you will only see these four options: Logo, 300, 1200 and PLC Sim.
Is it Schneider only?
What did you
Is
say?
the Schneider PLC on the
Schneider, they don't have the specific module for Schneider, but I hope this can be linked with Modbus, TCP and client server, or maybe OPC. There you have to use third-party software, but so far I don't think they have Schneider. Maybe they will update the software later on, but as of now that's not the option. Or maybe you can contact their control support, maybe they will help you to link it, but I'm not sure.
Okay.
Any other questions? I would be uploading the session after 24 hours, and maybe you'll find the link on the Facebook group, also on the YouTube. All right. So thank you for joining. I hope you enjoyed the session. If you are happy, sorry. Can you say that again?
I didn't get the last statement you said.
Oh, I said we are going to upload this video in our Facebook group, also in the YouTube. If you want, you can review that. And for next session, if you're happy with today's class, you are welcome to join.
Nice.
Sorry?
Yes.
For next session, I will put the information in the Facebook.
Sir?
Yeah.
Yes. I will update it.
All right. If you have anything else, you can also send me a message. So thank you for joining, and I'll see you in the next class. Have a nice time. Ciao. Bye.